Section 4.7 is on optimization, and optimization really involves finding maxes and mins, something that we've been, really working on a lot throughout many of the sections in this chapter. So we're going to start with the first example that isn't going to involve as much of the details that are listed out in steps 2 and 3. So as you read through these steps for solving optimization problems, they should look pretty familiar in terms of just general problem solving strategy in math. Drawing a picture, if one's applicable, which a lot of times in these problems it will be. Identify what you know and what you don't know. Then we're going to write the equation that we are trying to maximize or minimize. Now, this next couple of steps here, sometimes, a lot of times in this chapter, that may initially be in two variables that then we have to work on a little bit more in step 3 to get another equation that eventually lets us get back and get this in terms of one variable. But we're going to start with an example that is sort of just the big process here in terms of, finding our equation to min or maximize, and then just what we've done all chapter, finding critical points, and then showing that what we have found is in fact a min or a max in terms of whichever we're looking for. So let's jump in with this first example. It says you work for a food company that delivers some food items in open top boxes. Your boss tells you the company just got a great deal on some 20-inch square pieces of cardboard, and you have been asked to determine what size squares should be cut from the corners so that when you flip up these, basically these flaps, that you're going to have this open top box with the largest volume possible. So let's start with step 1, identifying what we know and what we don't know. So here's what I would say we know so far. They start off by saying we have these 20-inch square pieces of cardboard. So we have a 20 by 20 square here to start. What am I being asked to find? I'm being asked to find the size of these squares here, these little X by X squares in the corners, so that when I cut these gray corners out, what we have is going to be flaps that we're going to fold up, and then that is going to form our box. So here's what this is going to look like. So we're going to have, so let's just kind of draw in a dashed line here, and here, here, and here. All right, so this is now the base of the box, right? So this is really forming the base of our box. And then these are our sides that are being folded up. So these are going to be the sides of your box that are going to flip up. So I hope you can visualize what we're saying here. All right, so we are being asked then to come up with what size these little X cutouts should be to maximize the volume. So once we've drawn a picture and we've identified what we know and what we don't know, now we want to start with what we are trying to optimize. And in this case, we are trying to maximize the volume. So that is where we are going to start here. So we are trying to maximize, so I am trying to maximize the volume. All right, so we want to just think about, well, what is our formula for finding a volume? And in this case, the volume of a rectangular, or actually square, solid here. But in general, let's just kind of write it out in words here first. This would be the area of the base times the height. So that's what our volume would be. All right, so now the volume, we need to fill this in. So the area of the base, it is a square base. So it's going to be essentially the length of one side times the length of the other side, and those are going to be the same because it is a square here. So let's fill in what the length of these squares are going to be. So if you think about from, one side to the other, so all the way from here to here is 20, and then I'm going to subtract x from one side and subtract x from the other side. So if I start at 20 and I subtract 1x and I subtract another x, that is going to leave me with 20 minus 2x. So that is going to be the length of my side here. Or the length of the side. And then of course, because this is a square, on the other side it's the same thing here. So this is also going to be a 20 minus 2x in terms of the dimensions of each side of that square base. All right, so that is, maybe I'll just even draw this in blue here lightly. All right, so when I think about the area then of the base, that is going to be the 20 minus 2x times itself. So let's just write that as squared. All right, then times our height. Well, our height in this case, that is just going to be, when I lift up this flap, that is going to be this x right here. So as we lift up each of these flaps, this is now going to be the height of our box. And so the height is going to be x. So in this first example that we're doing, if you look up above in your notes here and you look at step 2, we've written the equation to be, in this case, maximized. And it says at this point, this equation is often in terms of two variables. Well, guess what? In our first example, it's not. It's already in terms of one variable. So we don't need to worry about step 3 in our first example. So now we just want to start to think about, well, how am I going to find the max of a function? Well, that's what we do when we think about setting our first derivative equal to 0 or does not exist to find critical points. And then we can kind of prove that we've gotten a max with a variety of tests. All right, so up to you, I suppose. You could, it's just a binomial squared. If you wanted to multiply that all out, that would be okay. I guess I'll just leave it like it is and just apply product rule. So I'm looking for my derivative, v prime. And so I'm just going to start here with my first function left alone. So the 20 minus 2x quantity squared times derivative of the second one would be 1 plus second function left alone, x. And then times derivative of the first one requires a little chain rule. So 2 quantity, 2 minus x to the first, and then times by chain rule derivative of the inside, negative 2. So this would have been, just kind of for emphasis here, the x left alone, and then this whole thing is the derivative of that binomial squared. All right, well, eventually I got to set this equal to 0 and try to find critical points. So I am going to think about just factoring out our GCF here. So notice that, and again, it's just a binomial squared. I think this is an example of something where you could probably get there efficiently by multiplying everything out as well. But I'm going to go ahead and just factor out my GCF. So that means my v prime here is going to be the 20 minus 2x. So factoring out that binomial. So this is my GCF right here that's being factored out from both terms. All right, now in the first term, what is left? A 20 minus 2x, one of those binomials. In the second term, a 2 times a minus 2, so a minus 4 and an x. So it looks like our v prime here is equal to 20 minus 2x and then times 20 minus 6x. And you could, I suppose, if you wanted to, factor out some GCFs from each of those, but I don't think there's a real need to worry about doing that here. These are going to be pretty easy to work with. So now we're looking for, again, where our critical points are, where we would have the derivative equal to 0, or where the derivative does not exist. I always want to be considering that. Of course, here there's no places where v prime is not going to exist. So we already have this factored. So as we think about setting each factor equal to 0, we're going to have our 20 minus 2x and then the 20 minus 6x equal to 0. So adding the x terms over to the right-hand side, we now have 20 equals 2x and 20 equals 6x. And then, of course, just dividing both sides by the coefficient of the x means dividing by 2 in the first equation. So x is going to equal 10. And then dividing by 6 in the second equation. So 20 over 6 would reduce to 10 thirds, or, think of it maybe as 3 1/3. All right, so here's the thing. A lot of times when you get done with these problems, you'll have some real obvious answers to throw out. Like x is a length here. That's a common thing. We might have a dimension, a length, a width, or something. It wouldn't make sense if I got a 0, let's say, or a negative. But I don't have that here. I have two positive, initially seemingly reasonable answers to consider. But let's look a little more closely here at this first one at x equals 10. If you think about making a cut of size 10, well, that would basically cut halfway in on both sides of this. So you wouldn't have a box anymore. You would just be kind of cutting this into 4 equal squares. Another way maybe to write this out would be if x is equal to 10, this would mean that your base side would have a length of 0, because it would be 20 minus 2 times 0. 2 times 10, which is equal to 0. And so that, of course, wouldn't make any sense. So we would end up with a base side equal to 0. And so this means, x equals 10 is not going to be the solution that we want to consider here. So we are going to throw out x equals 10 because we don't even essentially have a box anymore if we were to make cuts in a length of 10. So what does that mean for us? It probably means that this 10 thirds or 3 1/3 centimeters here is probably going to be our answer, right? But what do we really know at this point? All we really know is it's a critical point, a place of horizontal tangency. It could be a min, it could be a max, it could be neither. So we need to verify that this 10 thirds, so the last step is always going to be this verifying step. We need to verify that x equals 10 thirds is actually going to give the max value here. Now, how do we tell if something's a maximum? Well, we have developed several tests, and this is what step 5 here is about. You could identify a closed interval and do the test for absolute extreme on the closed interval. That's what I'm going to do here. That's probably the best, maybe. But I'm okay with you just doing first derivative test, or a lot of times I might do second derivative test, or maybe even graphing the original function. But we need to verify in some way. So we're going to verify that x equals 10 thirds gives us a max. And we're going to do that in this case. I'm going to write out the test I'm using. So we're going to say we're going to do this with our test for absolute extrema on the closed interval. So the test for absolute extrema on the closed interval. So this was, I think, the second section of this chapter. This was actually what we did before anything else, was the test for absolute extrema on the closed interval. All right, so the hardest part about this in an application problem is we need to identify our closed interval. Not integral, I'm sorry, interval. I do that a lot. Integrals is something that we're going to talk about in the next chapter. So interval. All right, so the first thing we need is we need what our closed interval is going to be in this case. Well, what makes this one not so hard in terms of coming up with this closed interval is we've kind of stumbled into it already. So obviously a reasonable lower limit for this cut is going to be 0. And we just found kind of the uppermost limit when we had to check that x equals 10. We can't have anything that's 10 or larger, otherwise we don't, we wouldn't have a box to talk about anymore. So this is going to be our closed interval here. That sometimes is the hardest part to come up with if you're choosing to use the test for absolute extreme on the closed interval. So what did this test say? It says find the critical points, and then it says take the values that are the endpoints, so the v of 10, the v of 0, and then in this case the v of 10 thirds. So we're subbing those values into the original function. All right, so v of 0, if I look up at the first one, that green x up there, 0 times the binomial is still going to be 0. And same thing if I sub in 10, sub it into the blue binomial, 2 minus 2 times 10 is going to be 0. 0 times anything is going to be 0. And then if I sub in 10 thirds, so I'm going to have 20 minus, this would be 20 thirds, quantity squared, and then times the 10 thirds. So hang on just a second, let me grab my calculator here and sub this in. Okay, so this comes out to be approximately 592.6. All right, so test for absolute extreme on the closed interval says the smallest value you get is the absolute min, and the largest value you get is the absolute max. And so the absolute max definitely occurs here at x equals 10 thirds. So the answer, again, make sure if they ask you for the volume, it would have been this 592 number that we just found. In this case, though, the answer is simply what's already boxed there. It was the length of the cut. Okay, so that's our first example. When we come back next time, we'll look at another example where we have to work a little bit harder to initially get the function in terms of one variable. So we'll get into a little more involved procedure with those middle steps in the next video.